Okay, that was quite a bit of shuffling around. You okay? Uh-oh. Okay, so last time we left off, we have the formation of the acetyl-CoA step. So we have the acetyl-CoA. This group is again going to be transferred from the acetyl lipoamide to the CoA. This will form the acetyl-CoA. So this is the acetyl lipoamide right here. That was that disulfide bridge that we'd broken. And then this is going to shuffle that acetyl group off onto the coenzyme A, and that will give us this acetyl-CoA. Notice again, that's still a sulfide linkage here, and so it's a thioester bond still, okay? And notice that we had made in the previous step that energy-rich thioester bond. We have maintained a energy-rich thioester bond. We have not actually gotten rid of that. We have just shuffled it off onto CoA. Okay? Same thioester type bond. So this is going to be catalyzed by the dihydrolipo transacetylase, literally transferring an acetyl enzyme. E2, that's that E2 region of this same polypeptide. The flavoproteins, this is going to be proteins that are tightly associated with FAD or flavin mononucleotide, or FMN, which would be the flavomononucleotide abbreviated. The dihydrolipoamide, this must be oxidized to the lipoamide to regenerate the active enzyme. 2 electrons are going to be transferred to the FAD prosthetic group of the enzyme, and then they'll be transferred off of the FAD, which has the electrons on it. That's the FADH2. They'll be transferred off to NAD+. And that's, again, going to free that FAD portion, prosthetic group, of our enzyme. So this is going to be catalyzed by the dihydrolipo dehydrogenase. By the way, the dehydrogenase E3 portion, the easy way to sort of remember that is we dihydrogenate, remove 2 hydrogens to form the disulfide linkage. Okay? And FAD typically accompanies, or NAD+, right? Typically accompanies these reactions. And so in this case, we get both. I know. So, yay, I guess. Does anybody have any questions about those so far? Okay. This is where we've regenerated that lipoamide, by the way, and we've shuffled that electron density off onto an NADH, which can do stuff with it. Okay. So the structure and function of the lipoamide arm of your E2 subunit is going to carry the substrates from the active site to active site. So we have the active site that makes that high energy thioester bond, and then what we need to do is bring it to another active site that's going to reset this process. Okay? So essentially we have 3 major things. Make the high energy thioester bond, right? Shuffle it off onto CoA so we can get the hell rid of it. And then we need to reset this. Okay? And that's basically what those 3 portions of your enzyme do, don't they? We have the E1, make the thioester, E2, shuffle it off, and bring it over, right? And then we have the E3, which is another active site, which actually has to reactivate that disulfide bond that we'll use to make the high energy thioester next time. Okay. It will increase the overall reaction rate for this reaction because, again, instead of trying to do it all in one go, you're breaking it up into multiple, much smaller barrier reactions, right? And so you can go across it much faster. This is going to minimize your side reactions. What did we say about that thioester linkages and these? Remember, you make like a carbonyl in here. You make a carbanion in here, a carbocation in here. Those would be incredibly reactive, right? If we were to release these and have them actually be exposed to anything else, those would react with basically everything else in the body, right? And so we preserve this by having a continuous linkage to this enzyme throughout the entire process. Okay? This is the lipoamide right here. This is why it's called a lipoamide. We have an amide and then a lipid. Yeah, I know. And the magic sauce, though, is this makes a long, flexible arm. This part right here makes a reactive disulfide bond. And this right here is a lysine side chain on our protein, isn't it? Okay. So the core of the pyruvate dehydrogenase complex is going to be formed by 60 molecules of your E2. This is the trans-acetylase. The trans-acetylase consists of 20 catalytic trimers that are going to be assembled to form a hollow cube. Remember when we just had 1 or 2 catalytic trimers and we're like, woo, here you go, 20 of them. So this is actually a pretty cool thing because this is a very recent assembling catalytic units to make large structures is a very recent thing for chemists to try to do. And so this is a neat, natural example of that you don't see as often. So each of the trimers is going to have 3 major domains. We have the lipoamide domain. This is a small domain that contains the bound, flexible lipoamide cofactor that's attached to the lase. The domain that's going to interacting with the E3 and the trans-acetylase domain. Here's this core right here. It's going to be surrounded by a shell of 45. This is the core right here. This is the shell here. 45 copies of your E1 and 10 copies of your E3. And so you can actually see portions of this right here detailed out in Abstractia, so you can see it easier. Okay? Notice, as far as molecules go, this is actually pretty big. 750 angstroms. Okay, so the trans-acetylase E2 core is going to be made up of 3 distinct domains. Here is that lipoamide we'd been talking about. That's that flexible arm right there. Okay, that your entire reaction is basically going to involve having that anchors onto stuff. This is the lipoamide domain. This is the domain that's going to interact with the E3 component right here. And then this is this trans-acetylase domain right here. So the E1, this is actually an alpha-2 beta-2 tetramer, excuse me. The E3, this is an alpha-beta dimer. And the E3 binding protein, which is E3-BP complex, this is actually going to be another core protein which will facilitate the interactions between the E2 and E3. This complex has reduced activity when it's missing, though you would still have activity because you would still have your cores of this portion of the protein. Okay? So step 1, the pyruvate is going to have a decarboxylation at the active site of E1. This is going to form your hydroxyethyl TPP. This will release CO2. Step 2, your E2 inserts the lipoamide arm of the lipoamide domain into your channel in E1, leading to the active site. Step 3, E1 is going to catalyze the transfer of the acetyl group to the lipoamide, and I'm getting ahead of myself. We're still acetylating. The acetylated arm. This is going to leave your E1 and enter the E2 cube to access the E2 active site. Step 4, the acetyl moiety is going to be transferred to your CoA. It is kind of funny calling this an acetyl moiety because it's such a small group, but yeah, I mean, yeah, it is. The acetyl-CoA, this will leave the cube, and the reduced lipoamide arm is going to then swing to your active site of your E3 flavoprotein. This is that part where we'll reset it. Step 5, the lipoamide is going to be oxidized by the coenzyme FAD. This will reactivate the lipoamide at this point. It can swing back and start doing a new reaction. The NADH is actually going to be produced with the reoxidation of the FADH2 to the FAD, resetting the FAD portion. Okay? Notice this has a lot of prosthetic groups. It's a pretty complex enzyme. Complex enzyme. Okay. You understood what I was saying, though, right? Okay. But it's really quite fascinating, right? You have to admit, did you think you were going to see something like that when you started biochemistry? Yeah. You didn't, did ya? 20 tetramers. Or 20 trimers, excuse me. That's good stuff. So here's actually our different domains here. And see the flexible arm there? Okay. So this is going to be the E2 portion, E1 portion, E3 portion. Remember the E3 portion has that prosthetic groups, the FAD. The E1 has the TPP. The E2 has this lipoamide, right? And so we have our prosthetic groups on each portion that we can see. The first part of this reaction, pyruvate, is going to have one of the CO2 groups chopped off it, and it's going to bind to the TPP here, right? And so that's that first portion of the reaction. And then our second portion, we have the disulfide bridge come over, and this is going to help us make that high energy thioester bond, right? And so we bring this on over. And then the third portion, we have made that high energy thioester bond. This is going to cause that to release from the TPP, and it's going to bring it back over into the E2 domain. Everybody see it okay? Okay, am I losing anybody in this? Fantastic. Fantastic. Okay, so the next part is we have the high energy thioester bond. We're going to have a CoA come in. This is just going to transfer that acetyl group off onto the acetyl-CoA now. And that's going to have this reduced disulfide on here. Now, this portion is going to end up going over to the FAD, which is in the E3 here domain. And that's where we're going to reset that by oxidizing it. Okay? And so we're going to oxidize this, transfer electron density off onto the FADH2 in this case now, and that will leave that disulfide right here on the lipoamide ready to do the next reaction. The next part that's going to happen is our NAD plus is going to take those electron density, that's going to move it away. This could be going to the citric acid cycle, the electron transport chain. This could be going off to do one of the other reactions that needs an NADH, right? Either way would work. Okay. By the way, have you fully absorbed how important the NAD plus versus NADH ratio is in all this? It shows up a lot, right? And this ratio determines which reactions can go spontaneously or not, doesn't it? It's not listed as a substrate because it's a facilitator, carrier, right? But it's incredibly important in, like 1/3 of the reactions? Yeah, something like that. So the citrate synthase, this is going to catalyze the addition of the acetyl-CoA and the oxaloacetate, yielding your citrate and CoA. Your reaction is going to be an aldol addition and a hydrolysis. It'll proceed through an energy-rich citryl-CoA. By the way, citric acid cycle. Ta-da! We got her name. Yay! It only took Dr. Clausen how many slides? God, that guy. Okay. So the oxaloacetate is reacting with the acetyl-CoA here. Remember, that's the one we just got rid of in the previous step. Notice that this is the beginning of our actual citric acid cycle, right? Before this, we hadn't actually entered the citric acid cycle, okay? Before we had been pyruvate, right? This is the first step that we're acetyl-CoA, we're going into the citric acid cycle. Okay, So what's going to happen is we're going to have our acetyl-CoA react with our oxaloacetate. Where's the oxaloacetate typically come from? So we're in a cycle, right? Meaning part of the previous product has to come back in, doesn't it? Yeah. And so this one comes from the end of the citric acid cycle, okay? We'll recycle that back in. So our acetyl-CoA will react with that oxaloacetate. This will give us citral-CoA right there. And you can see that it still has the CoA attached. It still is the high-energy thioester bond. We have just at this point linked it to the oxaloacetate. This gives a citral group right here. Okay? Citral meaning like citrate bound to something, right? The next thing that's going to happen is water is going to hydrolyze this very high energy bond here, right? And this is going to provide your energy for this reaction. And so what's going to end up happening is, again, we hydrolyze it. This is going to give it a carboxylate group here. And that's our citrate right here. Citrate having 3 carboxylate groups. Everybody see that okay? Okay. By the way, why is this not citric? Citric acid would be the acidified form, right? Yeah. So we're just at the citrate form here. Okay, so this is going to minimize our hydrolysis of the acetyl-CoA to the acetate and the CoA side reactions that can happen. The mammalian citrate synthase is going to be a dimer of identical subunits, each containing a small and large domain. The active sites are going to be in a cleft between the domains of the subunit. Your citrate synthase is going to exhibit sequential ordered kinetics. So the oxaloacetate will bind first, followed by the acetyl-CoA. The oxaloacetate then induces a structural rearrangement that creates a acetyl-CoA binding site. So remember, oxaloacetate first, acetyl-CoA, rearrange, binding sites available. Okay? Strict order. So again, this is the ordered binding of the substrates by the citrate synthase. We can actually see this very nicely in these conformational changes upon binding to the oxaloacetate. And so right here we have oxaloacetate binding. There's the oxaloacetate binding sites. And can you see how the yellow portions completely change their arrangement? Okay, to lock that in and incorporate that. Okay. And this is why you can't bind the acetyl-CoA without having those bound, is because that's going to then help you make the binding site for the next one, and then the complete binding is going to give you the active reaction domain. Step 1, the His-274 is going to donate a proton to the acetyl-CoA to promote the removal of a methyl proton by Asp375. This is going to form the enol intermediate. Note, by the way, enol intermediates being an incredibly common intermediate in biochemistry, right? We have seen this quite a few times now because they're very easy to establish in water, right? And they're very high energy, making them kinetically favorable for your next step. Okay. Step 2 is going to be the oxaloacetate. This is going to be activated by the transfer of a proton from the His-320, to its carbonyl carbon atom. Your step 3 is going to be the acetyl-CoA attacks the oxaloacetate to form a carbon-carbon bond, double bond. The His-274 is then going to be reprotonated, and the citral-CoA is going to be formed. Step 4 is going to be the His-274 participating in a proton donor to hydrolyze the thioester. Remember that thioester was that high energy bond in the acetyl-CoA that's going to be providing that final push of energy. Okay? This will yield you citrate and free up your CoA. CoA can then go back and get another acetyl. This right here is actually your substrate complex. And so right here we actually see the oxaloacetate. This is that proton being donated to it right here and making a hydrogen bond here to that carbonyl. This right here is actually the acetyl-CoA bound to this. we can see they're making hydrogen bonds here and here. And those hydrogen bonds will actually start pulling these different groups. So we have the electrons coming off that asp 375, pulling that hydrogen into a bond with the oxygen here to make the protonated carboxylic acid at that point, once it protonates. Okay, and this right here is going to be the hydrogen here is going to start giving its electrons into the bond here. That's going to protonate that carbonyl. And notice that's that enol formation. See the enol? Double bond here with an alcohol in it. Okay. Okay. And so that provides the enol formation. That makes this group more reactive here. So it can then start attacking here. Why did we need to make an enol, by the way? Okay, so this carbon here, what sort of charge would that have? Yeah, very positive, right, for our carbon. And if we make a double bond here, what's going to happen? The electrons are going to get pulled from that double bond up into that positively charged carbon, right? And we're literally forming, we're stabilizing right here, a very positively charged carbonyl, right? So that we can attack it and have the right orientation to attack it. And over here, we're forming an enol, and ene more specifically is the important part, high energy ene, that can donate electrons into it, right? So, nucleophile, electrophile. Okay, and so we're going to attack that carbonyl. Notice because we have this hydrogen readily available, and this group right here that has a very stable, easy on-off for that hydrogen, when the electrons come up on that carbonyl, this is actually going to pull the hydrogen here and form the alcohol instead. Okay? And so that will be the citral-CoA complex here. Note also that the electrons are going to get pulled off of this one over here. And again, that has that same group over here that's very stable and easy to put protons on and off, right? Because it has a lot of resonance structure. Okay. Anybody have any questions about that? Okay, fantastic. So the citrate is then going to be isomerized into isocitrate. I know. Isomers. That's why you needed organic 1. So the iron sulfur protein, this is a non-heme iron protein, by the way. Do not confuse it with heme. This is a protein that's going to contain an iron that's not bonded to a heme. One of the examples is aconitase, excuse me. Excuse me. So aconitase catalyzes the isomerization of your citrate into isocitrate. This is going to be through a dehydration step and then a hydration step. So this is kind of a cool reaction actually, because you don't see this very often, right? So what we're going to have is citrate is going to be dehydrated, excuse me. And so we're going to pull a water off, a hydrogen from one side and OH from the other. This is going to make a double bond. Now this is not going to be the most stable double bond ever, right? Because we have all these electron withdrawing groups all around it, okay? So it's going to be a fairly reactive double bond. And what's going to happen is we're actually going to, that's the cis aconite, by the way. Okay, the cis aconitate, the 8 part being these. Okay. So this is then going to have another water attack across this. Now, what do you note? That this is equilibriums on both sides, right? So what we're actually effectively doing is we're holding this in an area, and water pops off this sometimes, comes back on. It could come back on with the OH on one side and the H on the other, right? If it comes back on the wrong way, we collapse backwards, don't we? If it comes back on the right way, we go forwards, okay? And so this is kind of a cool equilibrium where basically we're just letting these waters pop off and on till we get what we want. And then it goes into the next reaction, right? So right here's the citrate binding directly to that iron sulfur complex of the aconitase, the enzyme that does the aconitate, if you will. And here's the iron sulfur complex, by the way. See, it looks like a little bit of a cube or something. And right here is the citrate actually bonding to it. And right here is actually, so when you have iron in solution, it'll bond water, but it actually makes the water more acidic. So you get OH minus quite often, and they're actually showing that very clearly here. So, so again, this is going to have the 4 iron atoms that are complex to 4 inorganic sulfides, 1, 2, 3, 4, and then 3 cysteine sulfurs, 1, 2, 3. Is it okay? The one iron atom is the available to bind the citrate. The others just make the structure and help regulate the flow of electrons, because you can have the electrons flow down onto these irons fairly easily. Okay? And all of that is right there. Okay? Can you all see that? Binding site, okay? Okay. So that isocitrate dehydrogenase is going to catalyze the oxidative decarboxylation of isocitrate. This is going to form an alpha ketoglutarate and the high transfer potential electron carrier NADH. This will proceed through an unstable oxalosuccinate. Your CO2 is going to be released from the oxalosuccinate to yield the alpha ketoglutarate. This is one of your oxidation steps, by the way, which means it's very important for several reasons. Number one, anytime you see an NAD, FAD, any of those things, don't think of those as being separate. What did I tell you the FADs and NAD pluses are? They're joints, aren't they? They're joints that are connecting you with what? The electron transport chain, right? Yeah. So these are points where we're coming back into the electron transport chain, okay? Don't think of them as separate. They're joined here, okay? Those are your real indicators. Hey, neon sign. I am transferring electrons, right? I am building up H plus concentration, okay? I'm going to go directly with my energy and put that towards ATPase, right? Okay. Or ATP synthase, more correctly. And the other part that actually tells you some of this is CO2. When CO2 escapes, that's going to diffuse, isn't it? And so these are times where we're committing this big time, aren't we? Okay? This is going to have a hell of a time going backwards because CO2 is going to escape. We're going to transform that very rapidly into carbonic acid. That's going to go through our blood. We're going to transform it back and breathe it out, aren't we? Okay? And so these are very good committing steps because the CO2 freely diffuses through your membranes. You don't have to do anything other than breathe out so you don't build it up. So anyways, this is the isocitrate. At this point, we had transformed that, swapped that OH over. This is going to be the NAD plus coming in. This is going to then have an oxidation where we take the OH here and the hydrogen here, and we go to a carbonyl. Now notice the hydrogens actually come off onto the NADH and an H plus. Remember again, this sometimes is called NAD plus and NADH2 plus. Okay? Because you can see why. Yeah. So anyways, this is our carbonyl now. Note the carbonyl is that red one. This right here, which is that other carboxylate that was in the middle there, was always kind of the high energy one because it's in between the other carboxylates, right? That's where your lowest energy, your lowest electron density would exist. And so this one right here is going to be the one that we're actually going to remove as CO2, okay? So we oxidated this further. That's going to make this even higher energy. An H plus can come in, and this is going to give us the CO2 here, okay? Because the electron density transfers 1 onto the hydrogen here. The hydrogen is going to take its spot on that carbon right there, okay? Okay. That right away is oxalosuccinate right there. This one right here is alpha ketoglutarate, okay? By the way, what's the alpha keto come from? Okay, if this was first group, this is alpha, right? Ketone. Glutarate. Okay. Okay. So our alpha ketoglutarate dehydrogenase complex is going to catalyze the oxidative decarboxylation of our alpha ketoglutarate to succinyl-CoA. This is going to yield our NADH. And here again, that's the alpha ketoglutarate that we had just finished. Notice again, we have that CO2. This is sorry, got it. I mean, it will be a CO2, right? This is going to be that carboxylate. Again, it's attached to a carbonyl. This is a very high energy group right here, isn't it? Okay, we have something that's very positive carbon attached to a very positive carbon, don't we? Okay, and so our NAD plus is going to come in. We're actually going to bring back a CoA here. Okay, remember that these CoA reactions, they're all happening in that matrix. They're not actually separate environments, are they? So we have this CoA freely as a resource in that matrix, freely floating about. Okay? Okay, and so what's going to happen is that sulfide on the CoA is going to come in here. It's going to attack this, and this is going to allow the CO2 to release and a hydrogen to release. Remember, this had a hydrogen on the sulfur. Okay? And that hydrogen is going to get transferred to the NAD+, giving us NADH. We'll release the CO2, which will diffuse off. Goodbye. So meaning this goes to completion, right? This doesn't go equilibrium. And then this is going to give us succinyl-CoA. My God, the damn CoA came back, didn't it? No. So your E3 component is actually going to be identical in both of these enzymes. So remember our wonderful E3 domain? We're bringing it back again. Okay? I know you loved it so much. I went body 10,000 or 50,000 years ago. Bring it back. So the alpha ketoglutarate and pyruvate, these are going to be alpha keto acids. Note again that we're just using that same terminology again, alpha keto, meaning right off of that first carbon, right? Acids, carboxylic acid group there. So both reactions are going to include the decarboxylation of an alpha keto acid and the formation of the thioester linkage with the CoA that's going to have a high transfer potential. The reaction mechanisms are entirely analogous. So here we have pyruvate plus CoA plus NAD+. We have the pyruvate dehydrogenase complex. This is going to go to acetyl-CoA, CO2, NADH, and H+. Over here we have another alpha keto acid, in this case alpha ketoglutarate, plus CO2 plus NAD+. We have the alpha ketoglutarate dehydrogenase complex. Notice again, substrate dehydrogenase complex. Okay? And then we get succinyl-CoA plus CO2 plus NADH. Cool, huh? You don't have to remember everything separately, as it turns out. We get to repeat stuff too. So the succinyl-CoA, this is going to be a synthetase, catalyzes the cleavage of a thioester linkage of your succinyl-CoA. This is going to yield succinate. It's going to be coupled to the phosphorylation of ADP or GDP, either one can be used in this case, because the delta G naught prime for the hydrolysis is actually going to be comparable to that of ATP. So this reaction is readily reversible. You can actually use ATP to go backwards and link this back onto the CoA. Remember that we talked about that thioester bond being very high energy? That actually gives you a great example of exactly what sort of energy this has. Okay? It's pretty close to an ATP going to an ADP. Okay? And that's actually what we end up doing. We literally take an ADP, put a P on it, an orthophosphate, release the CoA, and that gives us our succinate. Anybody have any questions? So the mammals have two isozymic forms of that enzyme. We have the GDP requiring enzyme. This will be predominant in tissues performing anabolic reactions like the liver. The GTP is going to be used to power the succinyl-CoA synthesis. The ADP requiring enzyme is going to predominate in tissues performing large amounts of cellular respiration, things like the skeletal and heart muscles. And so, yes, that's a little bit weird, isn't it? Keep in mind that the G and the A portions, they can actually interfere with your specific binding, okay? Because they are slightly different bases, right? They have different hydrogen bonding patterns, etc. The nucleoside diphosphokinase. So the nucleoside diphosphokinase, it's going to catalyze the transfer of the gamma phosphoryl group from any nucleotide triphosphate to any other nucleotide diphosphate. This is the one that allows for the adjustments of concentrations to meet your cell's needs. This is that overall class of enzyme here that's going to, this is the enzyme that allowed you to go like, I have too much ATP, I need GTP, okay? Or I have too much UTP, I need whatever TP, okay? This is the one that does that. This is going to keep your concentrations in your cell near equilibrium with one another because it's going to speed this equilibrium up. Thus, whatever equilibrium state you would have achieved will just be achieved faster, right? Everybody understand that overall reaction? Okay. So this is a clear example of energy transformation. We have an energy that's inherent in the thioester molecule. This is going to be transformed into the phosphoryl group transfer potential that we had normally been talking about. The reaction is actually readily reversible. It has a delta G naught prime of negative 3.4 kilojoules per mole. Remember, most reactions are up in the 80s, right? So a negative 3.4 is almost nothing, isn't it? That's very, very near spontaneous in either direction equilibrium state, okay? So the formation of ATP at the expense of the succinyl-CoA, this is going to be an example of substrate level phosphorylation. This right here is going to be your mechanism for your succinyl-CoA synthetase. It's going to allow the formation of your phosphoanhydride. It's through the phosphorylated enzyme intermediate here, which will be done here. So here's our succinyl-CoA. Again, that's that phosphate group right here. And this is the histidine right there. So what's going to happen first is we're going to get an attack on that carbonyl with the thioester bond. This is going to be with an orthophosphate, which is that free phosphate right there. That was that PI. This is going to allow the release of the CoA. At this point right here, we're going to have the succinyl phosphate. So this His group right here is actually going to donate some of the electron density that would have been in this lone pairs normally on this nitrogen. This is going to go on to that phosphate right there, the phosphorus portion. And this is going to allow the release of the electrons onto that oxygen there. Note that that takes that thioester and turns it into a succinate, which has the carboxylate there. See that negative oxygen? Okay, now this does leave this not quite phosphate, 3 oxygen that will become a phosphate again, bound to that nitrogen right there. Now this is stabilized by the resonance forms that can be taken on by this group here. And that's why these His groups are very, very commonly used for this sort of stuff, right? Because they can have those positive charge and distribute that positive charge throughout the whole ring, okay? Now, this right here is going to, again, allow a conformational change. This is what you're seeing right here. See the conformational change? Okay. And then this is going to allow ADP access to this more energetic, going to become a phosphate group. Okay? And so this is then going to attack the ADP, giving us ATP and resetting our His. Anybody have any questions about that? Okay, fantastic. So step 1 is going to be the orthophosphate attacking the succinyl-CoA. This will displace the coenzyme A, generating your succinyl phosphatate, a energy-rich compound, of course. The His residue is going to act as your moving arm. This is going to remove the phosphoryl group, forming the phosphohistidine. This will release the succinate. Step 3, by the way, notice that at this point we've actually gotten rid of what is called the substrate. Okay? At this point we have actually completely gotten rid of the substrates. All that's left is the orthophosphate attached. Okay? So step 3 is going to be the phosphohistidine. This is going to swing over to the bound ADP. Step 4, that's that rearrangement, by the way, down here. Okay. Step 4 is going to be the phosphohistidine transferring the group to the ADP. This will form your ATP. Note that you don't actually reset to step 1 at this point. We are actually kind of ignoring the reset portion for this. Okay? The succinate dehydrogenase, the fumarase, and the malate dehydrogenase, these are all going to catalyze the successive reactions of 4 carbon compounds. These will regenerate the oxaloacetate, resetting our cycle. Remember, our cycle has to start with an oxaloacetate and an acetyl-CoA, right? The FADH2 and NADH are going to be generated during these steps. What are important about these compounds? Those are... Exactly. Yeah, we're transporting electrons. Yeah. Those are basically the little wires connecting our generator to what we're going to use it for, right? Okay. So once regenerated, the oxaloacetate, again, initiates another cycle, and we keep going on and on and on with those, okay? The succinate here, so that's that succinate. This is going to have these 2 hydrogens here. These are going to come off in a dehydrogenation reaction, which is why this is dehydrogenase, right? Succinate dehydrogenase being the enzyme. This is going to use FAD going to FADH2 to transport the electron density, and it will leave this fumarate right here. The fumarate is kind of an interesting compound. It has that double bond between 2 carboxylates, which looks pretty interesting. This is actually going to have a hydration. So you're going to react water across this. That's going to further oxidize this and give you malate. By the way, that's why this is the fumarase. Literally, it's just an enzyme that's going to work on fumarate, and it's going to do a hydration reaction. If we didn't care how fast this went, this would happen on them. Doesn't need an enzyme to do. Just faster, right? Speed it up. So this is going to give us malate. The next step is going to be the malate dehydrogenase enzyme. Again, the big hint here is that you have an NAD, FADA, those tell you, hey, oxidations are happening. So what's going to happen then is we're actually going to take this OH here and we're going to get the carbonyl. Okay? And so this is going to go down to the carbonyl. Again, that's another oxidation. We get the NADH out of that, transporting the electrons, and that gives the carbonyl right there, which is the oxaloacetate, actually. Bless you. Bless you again. So the succinate dehydrogenase, this is an iron-sulfur protein again. It has an isoalazine ring of FAD that will be covalently attached to a histidine side chain. This is going to be embedded in the inner mitochondrial membrane. Anybody know anything about the electron transport chain yet? Okay, so you already kind of see where this is going, don't you? Yeah, you've had that a little bit before, because that inner mitochondrial between the two membranes, what is that going to involve? So notice that this was attached to the inner mitochondrial membrane. So between the inner mitochondrial membrane and the outer mitochondrial membrane, what do we end up doing to that? Yeah. Exactly. That's where we're going to build up that proton gradient. So you can kind of see this is where we're starting to do the pumping process. This is part of that. So this is directly associated with our electron transport chain. When you look at the electron transport chain, we're going to call these complexes, but recognize that look deeper, look closer, because you'll actually start seeing that these enzymes show up in both places, okay? Those are where those are actually connected, okay? And they're connected through the wiring that is the FAD-NAD, right? The FAD is going to be a hydrogen acceptor because the free energy change is actually insufficient to reduce NAD+. So this actually has real meaning of using FAD here. You can't use NAD+. It won't work. The enzyme attached to the FAD here, remember that these are coenzymes, right? So when they're actually in use, what are they going to appear as? I know we oftentimes don't mention it, but in reality, the NAD pluses and FADs are almost always attached to an enzyme when you're looking at them. Correctly stated, they should have been EFAD, ENAD plus, okay? Denoting their complex to the enzyme. So this is going to react with the succinate. This is going to form an equilibrium, which is going to take you to FADH2 on that enzyme, and the fumarate, which is that product in that first step. Right there. Okay, and so the fumarase, this is going to catalyze the stereospecific trans addition of the H plus and OH minus. This is going to yield only the L isomer of malate. Remember that almost all enzymes, this is highly stereospecific because enzymes themselves are stereochemically active, right? They have only a single stereoisomer they'll make, usually. So the fumarate here, we're adding an OH on one side, we're adding an H plus on the other. That gives us the L-malate right there. The malate dehydrogenase is going to catalyze the oxidation of the malate, yielding oxaloacetate and NADH. This does have enough energy to go ahead and do the NADH here, NAD plus to NADH. And by the way, the oxaloacetate being the product that we plug back into the citric acid cycle. So we've actually completed that cycle. The delta G naught prime, this is going to be significantly positive in this case. So our delta G naught prime is actually 29.7 kilojoules per mole, even though we're generating that NADH here. So this actually has a very high spontaneity. The reaction is actually driven by the use of the products, the oxaloacetate by citrate synthase, and NADH by the electron transport chain. So again, remember that, I guess I'm out of time, but we'll start on here, okay? Think about this delta G and how we have to actually pull that through, right? Okay. And part of that pulling that through, remember our thioester bond that's very high energy? Ooh. Yeah. Okay. You all have a wonderful weekend. I'll put a video up. If I don't get my email sent out, because I tried to do it while I was walking away from the building, it will definitely be out there by Saturday.